So far, we have basically understood about some of the foundational concepts of regression. And now from here, we'll try to understand what is classification. Now, we already discussed classification. We already briefly discussed what is classification in the session yesterday. So we know that in regression, we are trying to predict a number. Whereas in classification, what is you are trying to predict a category. So we know that. We know what is classification. What we are doing now is we are trying to give you a slightly more pictorial understanding of classification. Okay, how do you think of classification a little bit more pictorial? See, even for regression, if you remember, I told you that in regression, the output is a number. We are always trying to predict a numeric output. Regression, we are always trying to predict a numerical output, a numeric output in regression. But we also discussed a visual approach yesterday. What is regression visually? We are trying to find what is the line or plane or mathematical surface. Okay, so what is the line or plane or mathematical surface that best separates the classes? I'm sorry, that best fits the points. Right? All of you remember that, right? So in regression, the theoretical definition was, yes, we are trying to predict a numerical output. The practical demonstration, the visual demonstration was like that in regression, we are trying to find the line or plane or surface. I say surface because it doesn't always have to be a line. It can be non-linear also, right? So we are trying to find what is the line or plane or surface that best fits the points. That's regression. Same way we try to understand classification now. Okay. In classification, we are trying to find out what is the line or plane or surface that best separates the classes. Okay, so what is the line or plane or mathematical surface that best separates the classes? That's the way how we understand the core ideas of classification. Okay, so you have some data and you're trying to find out what is the line or plane or uh, mathematical surface that best separates the two classes. That's the way how we understand the core ideas of classification. Let's take the same example. Let's take a beautiful example here. So we have a use case of a self-driving car. Not, I mean, very simple analogy of a self-driving car we are taking here in this example. So we have the different attributes of the road conditions, which are steepness and bumpiness. So steepness and bumpiness are giving us the different attributes of the road conditions. How steep is the road and how bumpy is the road. Okay, so we are looking at the different attributes of the road conditions. How steep is the road? How bumpy is the road? And based on the different attributes of the road conditions, we are trying to predict the speed of the car. So based on the steepness of the road and the bumpiness of the road, we are trying to predict, will the car go slow or will the car go fast? Okay, so I repeat again, based on the steepness of the road and the bumpiness of the road, we are trying to predict, will the car go slow or will the car go fast? So once again, we are taking the entire historical data. So this is a whole bunch of historical data that we are considering. And you have all these different patterns that are playing out, you can see. So you're monitoring the car and you're training the car, because we know that we have to, in order to build a supervised learning model, we have to train the system over different data points, over different iterations. That's exactly what we are doing. So we are considering different instances. So you can see that when the road is less steep and less bumpy, the car is going very fast. Lots of greens here. Okay, so you can see every dot corresponds to one instance. So whenever the road is very steep and very less steep, it's not very steep and not very bumpy. So steepness value is low and bumpiness value is low. So whenever you are in this zone, the car is going fast, greens. And whenever the road is very steep and very bumpy, or either steep or bumpy, the car is going slow. That's the way how you train the car, isn't it? So it's like it's like you're teaching a kid how to drive. So when you're teaching a kid how to drive, you will first drive the car yourself, and only then the kid will learn. Right? So this is how exactly we are collecting our data samples. Right? In case some of you in this, in the audience are wondering that, hey, how are we getting this data? How are we collecting these data samples? This is exactly how we are doing that. So in order to teach the kid, we have to drive the car ourselves. And this is exactly how we will drive the car. If the road is not steep and not bumpy, we will go very fast. If it is steep and bumpy, we will go slow. That's it. That's how our data is right now. That's how we get the XY combinations. And once we have the input output combinations, you can see this is the categorical output variable. We will use some algorithm and we will build a model. Now, what is the model? The model will be an equation. It's a linear equation or a non-linear equation. And we also call it a decision boundary or a decision surface. Okay, so in the world of classification, that model that you end up building, that model is also called a decision boundary, or it is also called a decision surface. That is what the model refers to here. So we take the data, we use some algorithm, and we build a model. And that model is a decision boundary or a decision surface. So this is what you end up learning in the process. So when you do model.fit, this is the boundary that you end up learning. This is the result of model.fit. You end up learning the decision boundary. That means you are able to separate the reds and the greens in the most optimal way. This is the line of best separation. Yesterday, regression was line of best fit. We are trying to find the line that best fits the points. In classification, you are trying to find out what is the line or plane or surface that best separates the classes. You are trying to find out the best separation. What is the line that best separates the reds from the greens? You're trying to find the separation here. And once you get the model, once you have the final model or the decision boundary, once you have this thing, next time I give you a new data point, let's say you have a new instance of a car, and for the new instance of the car, you have steepness is 0.3 and bumpiness is 0.4. So now you have the new instance of the car, and you want to predict what is the speed of the car. So you will see that, hey, I think 0.3, 0.4 is on this side of the line, so the model will predict fast. That's the way how the fit and predict will happen for classification. So very important. We talked about the pictorial understanding of classification here. So yes, we are trying to predict a category, but how do we think through it? How do we think through a classification problem? What is it? What is actually going on behind the scenes in classification? So in classification, we are trying to find the line or plane or surface. What is the line or plane or mathematical surface that best separates the classes? We are trying to separate the reds from the greens, right? We've got lots of reds, we've got lots of greens. So we are trying to find out what is the line or plane or mathematical surface that best separates the classes. That's what you're trying to do in classification. You're trying to find the surface of best separation. Whereas in regression, if you remember, we are trying to do a best fit. We are trying to find what is the surface that best fits the points. That's what we are trying to do in regression. Okay, I think it's best understood. It's the best way to learn anything is through lots of examples, lots of pictures, and that's what I also believe in. So let me show you this beautiful example of regression and classification pictorially. I showed you one example yesterday, and I'm going to go to Google and show you a couple of images. This is the image I was trying to show you. Okay, look at this. Yeah, the handling is a bit coming a little hazy, but you get the idea. I think you get the idea what I'm trying to relate to. Yeah, let me open it up. Okay, I think we get the understanding here. Let me just open up from this image itself. We are able to follow. I think this is good enough to understand. So you can see in the regression part, what are we doing? We are able to like this is the part we already saw in the conversation yesterday. I think we understand that in regression we are trying to find the line or plane or surface that best fits the points. That's what we are doing in regression. So what is the line or plane or surface that best fits the point? So overfitting will look somewhat like this. Okay, underfitting will look somewhat like this. Good fit will look somewhat like this. Okay, so this is how we can understand the ideas with respect to regression. Now, if you go to classification, the idea that I just now talked about, if you go to classification, underfitting will be like this. You've got lots of oranges, lots of blues, Underfitting is where you're not able to learn the relationship at all. So you're trying to ultimately find the separation between the classes, right? You're trying to find the separation between the orange and the blue. So you're not able to find the separation. So, you're not able to separate the orange and the blue in the training itself. So it's a very, very bad model. Overfitting, you're doing too well. On the training data, you get a perfect separation. That's overfitting. Too complex, too many twists and turns, but you do a perfect job in the training data. Right fit is somewhat like this, more or less. Okay, okay. That's the way to pictorially understand regression and classification. So regression is always best fit. You're trying to best fit the points. Classification is best separation. You're trying to best separate the classes. Okay. Now, what we will do is given this idea, but everything else remains exactly the same. So many of the core ideas that we covered yesterday, train, test, plate, the process of building a machine learning model, uh, some of the correlation concepts, histogram, power transform, the ideas of encoding that we talked about today, like one-hot encoding, label encoding, how you use pipelines, overfitting, underfitting, the process of using cross validation, all these core ideas remain exactly the same.